Okay, so I posted this document up on CCLE. It's got a basic description of what you can expect for the midterm exam. And I know it feels like the class just started, but it's summer session, so we're already at our halfway point. A 6-week course, it's already halfway. And so, I mean, it just goes fast, right? So anyway, I know it's a little bit different from what I've written in the syllabus regarding the timing. I think in the syllabus I said I would release the midterm after class on Wednesday and have it due Friday. I decided I'm going to release it Friday and have it due Saturday. Okay, so it'll come out Friday at noon and we'll close Saturday at 11:59. And this is California time, so wherever you are in the world, make sure you give yourself enough time. The exam is timed. You will have 2 hours. So once you start it, a 2-hour timer begins. And so, you want to make sure you start, think how long, make sure you start it before 9:59 on Saturday. Otherwise, you'll have less time, right? Okay. Or I'm not quite sure, maybe it'll give you 2 hours, but then it'll say you're late. So, either way, you don't want that to happen. Okay. So just make sure you plan ahead and make sure you give yourself a 2-hour window. Okay. And then if you have accommodations, that those will also be included. I can inform grade scope of those kinds of things. And anyway, you will take it on Gradescope. It's going to be an online assessment. There's a little video I included just showing how these things work. It's basically it's a web page, right? And some of the things will be short answer where you kind of type in a number, or you type in an answer. You can also have multiple choice questions. I don't know if I'll have many multiple choice questions. I'll think about it. But and then there's also going to be places where you can kind of type in it's meant for like typing in a paragraph of text, but in those sections, I'm going to have you type in basically code. Okay. It's open book and open note, and you're allowed to use R. You can read documentation. What you're not allowed to do is you're not allowed to talk to other students. You're not allowed to share information about the exam or things like that. Okay. And basically we'll cover the lectures we've had, including today's lectures. So that's a total of 4 lectures, and that's it. Okay. I recommend at least taking a look at homework 3 and trying to do some of those things, because I think that will be relevant for doing the exam. You don't have to have it completely done, but I think if you do some of the exercises in homework 3, it'll provide some good practice there. Okay. And so here are just kind of like example questions that these are not going to be the questions that appear on the midterm. Obviously they'll be different, but these are, this gives you an idea of what kind of questions I could ask, right? And so, some of the questions will be like, what is R going to produce? And now these questions, normally during in-person exams, these are actually like significant questions and meaningful, because you don't have R in person, and you have to think about what it's going to produce, right? Here, you can type in the question into R, and you can see what R will produce, right? So that takes away a big portion of the kind of the difficulty of these questions. So I'm going to, some of these questions I'll put in a why. I'll say like, why is this going to happen? And also just to kind of like, I don't know, add a little bit of friction. Perhaps the question will be presented like a screenshot. So you can't just copy and paste the code straight into R, but you have to at least type, like if you want to enter it into R, you have to type it by hand rather than, it might be presented as a screenshot. At least that, where, the student who's at least aware, can kind of work through these things a little bit, maybe a little bit faster or something. But but that's kind of what we have here, right? So, what happens if you combine NA with null, right? And what will the length of X be? Well, the length of X will be 1, okay? What if you combine NA with character 0? What will the length of Y be? Okay, well, the length of Y will be 1, okay? Because null is length 0, and if you try to combine that, the result is going to be X is a length 1 vector, and character 0 is also length 0, and when you do that, the length of Y is also going to remain 1. Okay, now if you ask, is X going to be logical? That's going to be true, okay? The NA is a logical type, and if you combine it with a null or something, it's going to remain logical type. Whereas Y is logical is going to be false because NA starts off logical, but when you combine it with a length 0 character vector, it's going to coerce the NA into a character type NA. And so Y is going to be coerced into character type, and so is logical is going to be false, okay? And so, I'll have like a Y, and you'll basically say, Y gets coerced into character type, or the NA gets coerced into character type in Y or something like that, okay? So that might be some kind of question, something like that, right? I think this is a good question. I don't know. Who knows? Okay. And then there's the other questions. You'll write a few lines of code, right? So I'll say like, and basically, you'll have a little window where you can enter in some stuff. And as far as the complexity of the problems, most of these coding questions should be fairly simple, where you can answer your question in just like a few lines of code, like 5-6 lines of code or less or something like that. If you can't figure out a solution that takes only 5 or 6 lines and your solution takes 20 lines of code, that's okay. You're not going to lose points, but this is just to kind of give you an idea of like how difficult or how complex the questions will be. Okay. Now, what you're going to do, what I recommend is you like write your code in R and test it out that it works. And when you get your code working, you're going to copy and paste it into the text box on Gradescope. Okay, you're going to copy and paste it into Gradescope. And then when we grade it, what we're going to do is we're going to copy and paste the code from your text box, copy it into R, and try running it. And it should run, right? And so if what you copy into the text box produces errors, and when we copy it into R and try to run it and it produces errors, you're going to get a 0 for that question. So make sure what you copy over is good, right? Sometimes when you produce stuff in R in the console and things like that, it inserts these little pluses or these symbols and extra things. Make sure you don't do that, right? So, for example, let's say, all right, so, you got like an R script and you want, let's say I say, write a, okay, so here's the thing, right? It says, I provide a series of text strings and ask you to write a line of code, or I ask you to write a vectorized function that will accept a vector of values, and you can calculate the corresponding outputs from a piecewise function or something. Okay, so let's just say f is going to be a function of x, and we're going to do if else x greater than 0. What we want to do is we want x squared. Otherwise, we want negative square root of x or something like that. Okay, so we'll do this, right? So what you want to do is you want to copy and paste this. You don't want to copy and paste this stuff down here, because if you copy and paste this stuff down here, you get these little extra symbols, and that's gonna choke it up. Okay, so copy and paste this stuff, right, into the text box. You'll be good, because what we're going to do is we're going to just take what's in the text box, basically put it into an empty script, run it, see if it works. Okay, and if you copy and paste from the console, this puts in all of these extra symbols, these pluses and these little whatever greater than signs. So don't copy from the console, copy from whatever script you're writing. Okay, and just make sure it's correct or something. Okay, does that make sense? what we're going to see on the on Gradescope? Okay, then good. Okay. All right. Well, we'll let's get started. We got this is a huge PDF. Here it says 128, but it's like 208 because like some of these slides like have multiple things. Okay. So first we got to talk about dplyr. Now, some of you have already seen dplyr. Depending on who taught stats 20, when you took stats 20, you might have already had exposure to dplyr. You might not have. You might have seen dplyr from other places, but anyway, it's worth covering again. Just because I think some of the functions in dplyr. Now, I think there was a question on CampusWire, and I can respond to it. And I said, use dplyr to answer these things. And somebody said, like, well, can I use sum or things like that? Yes, of course, you can use base R functions and things like that. So I do want you to use dplyr, mostly for kind of like the grouping of producing groups. Okay. So anyway, you do library dplyr or library tidyverse. That's going to load up dplyr, and basically, the whole point of dplyr is it's going to make this part easier, right? When you're trying to work with data, you got to figure out what you want to do. You want to put them into some kind of program that the computer can run. And what dplyr does is it says, you know what? Basically, all of the things that you're going to try to do can be described down to basically a set of verbs that it calls verbs, right? You can filter, you can select, you can group by, you can summarize, and it kind of forces you to think in terms of these kind of simple verbs, right? Pretty much, like I think like if you were to take like a mechanical engineering course or something, like basically all mechanical machines can be simplified down to, I think there's 7 simple machines, right? Like the inclined plane and the wedge, which is just a moving inclined plane, things like that. And basically with dplyr, you have a set of verbs and you think about this, right? And so these are kind of the verbs that we have. We've got select, we have filter, we have mutate, we have arrange, we have summarize. These are kind of the most important verbs. There are, maybe secondary verbs that go with it. And a lot of these work with the other verb that is called a group by. Okay, so select basically selects variables. Filter will filter the cases or the observations. Mutate creates a new variable. It mutates currently existing variables into new variables. Arrange will basically sort or order the things, and summarize will take multiple things and summarize them down to a single value. And that's basically what we're trying to do. Now, all of these things assume our data is in tidy form, which we talked about last week. With all of these holidays, the last time we met was an entire week ago. So last week we talked about tidy data, which says, each observation needs to have its own row. Each variable needs to have its own column. And so dplyr assumes your data is in tidy form. Okay, if it's not in tidy form, you got to use tidyr to get your data into tidy form first. Otherwise, this stuff's not going to work with it. Not going to work. Okay, there is a cheat sheet, which I think is pretty great. So you can download this, and yeah. So all of this stuff, the tidyverse, is kind of the creation of Hadley Wickham. Hadley Wickham is, this probably one of the most important contributors to using R for data science and data analysis, and he's produced so many things. He's from New Zealand, and so some of the verbs and the spelling. So like summarize is spelled with an S, and that would be kind of the New Zealand or British form of spelling, whereas in the United States we use the letter Z in summarize and things like that. And I think it now allows for summarize to use the Z spelling as well. But but the original function is written with an S, okay? But we have to thank Hadley Wickham, who is one of the chief scientists at our studio, and excellent software that they've produced. All right, so let's go ahead and take a look at a few examples, okay? And so one of the data sets in available in the tidyverse is this Star Wars data set, okay? And it contains information about various characters from the first 7 Star Wars movies, okay? So there's now 9 Star Wars movies in the kind of the Skywalker saga, as well as 2 spin-off movies, Rogue One and Han Solo, or it's just called Solo, and things like that. And apparently whoever compiled this data set did it after The Force Awakens, but before whatever, The Last Jedi. Anyway, so it contains information about some of the characters that we see, their height, their mass, their hair color, their skin color, their eye color, their birth year, their sex, along with 6 more variables. We have gender, homeworld, species, which films they appear in, which are lists, which vehicles they've commanded or driven, which is a list, and the starships that they've, I guess, commanded. I don't know, whatever. Okay. So you have things like Luke Skywalker. He's one of the main characters in the original trilogy, C-3PO, and things like that. So anyway, we've got this. And so we could say, you know what, let's just take a look. Let's select some of the columns, right? So Luke Skywalker appears in, it says 5 films, okay? So we have Tatooine is his homeworld, he's human, appears in 5 films. So the 3 original films, plus he appears in the 3rd movie in the prequels, Return of the whatever, the Sith movie. Okay, you're right. He's a baby in that one, and then also well, okay. So anyway, we've got that, and then C-3PO. We have this. Yeah, and he makes an appearance at the very end of The Force Awakens. Okay, C-3PO has been in 6 of these movies, R2-D2 in 7, so on and so forth. Okay, so we've got a bunch of these things, and this is what we see. All right, this dplyr always produces tables. Okay, now we've seen the pipe before, but the pipe basically, so notice here we've taken select from the dataset Star Wars, data frame, Tibble, Star Wars, when we want to select these column names, name, homeworld, species, films. What we can do is we can also pipe. We can take Star Wars and pipe it into select, okay? And what this does is it basically takes the thing before the pipe and puts it right into as the first argument of the next function, right? So from select, it says, select from what Tibble, and we're going to take it from Star Wars. And this allows us to kind of chain things because the output of select is a Tibble, and then we can then kind of pipe this output into another statement, and it will be working with this output rather than the original Star Wars, right? So if you want to create a pipe, you're going to hit Control-Shift-M on your keyboard or Command-Shift-M, as long as you're working in our studio, and it will insert a pipe, right? So here I can take Star Wars and I can say, select all the columns except for name, eye color, and birth year, right? We can do minus signs to say, I don't want these columns. And then I can take that output and pipe it into the head function, which will just give me the first however many rows I specify. Here I'm saying I only want the first 3 rows. And so that's what we have here, right? And so it gives me everything other than the name, the eye color, and birth year. Okay, you can also, so this is interesting, is you can use the colon notation in dplyr, and it's going to select basically from one column to the end column, right? So you can say select all the columns starting at name and ending in eye color, which will be name, height, mass, hair color, skin color, eye color. So however they appear in the data frame, you can kind of use colon notation, almost like, we're accustomed to using colon notation for creating a sequence of integers. But here we can kind of say, I want to go from starting here and ending here as far as the column names go, okay? And so it depends what order the column names are in, and it will do that, okay? We have special functions that go along with select, okay? So, as far as, we want to select columns that contain a certain character string, or starts with a certain character string, or ends with a certain string, or it matches some kind of regular expression, or you can say select everything. That's going to select all the columns. You can select a numeric range. As far as columns that are named, sometimes you import a data set and the column names are like x1, x2, x3. These are kind of not very helpful, but you can select them, and you can also use this one of, and you just kind of give it a vector of names that you want to select, okay? So here's just a few examples, right? So you can say, select all the columns that ends with the string color, right? And so so we want to select the name column along with any column that ends with color. So this will get hair color, skin color, eye color, okay? We can say this is a regular expression, and this says matches the string, the regular expression where it ends with the letter S. We want to select the name and all columns that ends with the letter S, okay? So this, I could have just done ends with character S, okay? But this is a regular expression that just says S at the end of the string, right? So we get mass, species, films, vehicles, starships. These all end with the letter S, okay? Here you can have a list of a vector of names, right? So maybe you have some other function that produces a vector of names of the columns, and then you can say take the data frame Star Wars and select all of the variables in this vector here, all right? Name, mass, height, and you can select them that way, right? So depending on some whatever workflow path you've got going on, maybe you'll end up doing something like that. All right, how do we feel about all of these select things, right? This is just a way for us to select columns. And I think that's fairly straightforward. Okay, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter D. D as in dog. D as in dog is your first view quiz answer. All right, continuing on with dplyr, we've got the function filter. Filter will allow you to select certain observations or certain cases. So in our case, in our Star Wars data set, each row is a character, right? So, at kind of its most basic, you can just say, I want to select the cases where the name matches this string R2D2, right? So we're going to say name is equal to R2D2. And there's only one character in the Star Wars data set with that name, R2D2, and here it is, okay? R2D2. There you go. Okay. You can apply multiple conditions, right? So here we're going to say, I want all the characters that are either humans or droids and have a height of under 175, okay? So, so we get these people and droids. These humans and droids, we get Luke and C-3PO and R2-D2 and Leia, and I guess this is Aunt Beirut and things like that, okay? And there you go. All right, filter can be used alongside regular expressions, right? So we will talk about string detect. String detect is going to return true or false if it matches a certain pattern, okay? So this is a regular expression, and so in today's lecture, we will cover regular expressions, but just for now, this expression means starts with a capital F. So this little caret F starts with a capital F, and basically it's going to go through the name column, and string detect will return true if it finds this, if it starts with a capital F, and it will return false if it doesn't. And if you use filter along with string detect, it will only return the rows that match this pattern, which will be character names that start with the capital F. And so I don't know who this character is. Finn is something, and Finn is one of the main characters in the Force Awakens, okay? But I don't know who this character is. But anyway, there you go. 2 characters from in the data set. Okay, so what you can do is you can also pipe results into each other, right? So we can take Star Wars, and then we can filter certain rows. So we can say, I want people that have no hair, hair color is none, and eye color is black. Okay, so we want characters with black eyes and no hair. Okay, and from there, we're going to then pipe and select only the columns, name, species, homeworld, hair color, and eye color, right? And so we can see, all right, so these are all characters. Oh, I'm sorry, this is or. All characters who either have no hair or have black eyes. Okay, so we get Darth Vader, who has no hair, but apparently yellow eyes. I didn't realize Darth Vader had yellow eyes. Okay, and then and Greedo is I guess a Rhodian species alien. Also, hair color is NA, not quite sure, and then but does have black eyes. IG-88 is a robot, has no hair and red eyes and things like that, right? So you have all of these kind of these non-humans, although you do have Lobot, who is he's the bald guy with the little like, I don't know, he's like okay, no hair and blue eyes. Lando Calrissian's like kind of head of security, I guess. All right, so you have this. Okay, this is that's that. Okay, so we're piping the results of filter, which will just be these 38 rows and all the columns, and we're piping that into the select, which then only selects these 5 columns. So the result is going to be 38 rows, 5 columns. All right, now if we want, we can also arrange the results using arrange. So we can say, you know what, I want to get, we're going to arrange by descending birth year. Okay. And so in the Star Wars universe, I think they use the Battle of Yavin as the kind of the 0 point, right? So when the Death Star explodes, that's year 0, and Yoda was born 896 years before that, and that's based on kind of a throwaway line in the dialogue where Yoda says, you know, when you're 900 years old, you are not going to look as good as me. And and apparently that was, I don't know, maybe 4 years after the Battle of Yavin. Okay. And you have Jabba the Hutt and Chewbacca, and all, these are all super old characters and things like that. Okay. So these are your... so we've arranged by descending birth year, and we said break ties based on mass, okay, in ascending order, okay. You can also, so depending on the results, you can also use slice, which is a, you know, a little bit of a stranger thing, but you can just say, I want rows 5 through 10 or something like that, and you can just do slice 5 through 10, and this will This will select rows based on their location in the original data set. Okay, and but slice sample is probably a little bit more useful than slice itself. And that's like, I just want to select some random rows, right? You just want to select a sample of rows from your data set, and you can do slice underscore sample, and you specify how many observations you want in your sample. And so here we say 5, and here's a random sample of 5 observations from the data set. So this is a handy thing, which is often useful, because sometimes you want to check if your your operations did whatever it is you want correctly. And if you only look at the head, you're getting a very limited view of your data set, right? Because maybe the head of your data set, fits a certain category or description, and maybe it works fine on those things. But if you take the results and look at slice sample, you can kind of you get a glimpse from different portions of your data set, and that's a useful thing. Okay, you can also do slice min and slice max. It's pretty much the same thing as doing a range and then slicing and then taking the head, right? But slice min and slice max kind of combines these operations for you. So you can just kind of, whatever you've done, you can then say, I want, give me back the 3 rows with the largest mass, right? So slice max mass, 3 rows, and it's going to give you the 3 heaviest characters in the data set. Okay. Okay. So that's for selecting all of your rows, and so let's take a look at creating new columns, all right? Which is a lot of times something we need to do, right? So one thing is this is silly, but we can just take the height and we can turn it into inches, right? So this is height in centimeters. We're going to divide by 2.54 to convert them into inches. And we can say, I want the first row, and that gives me this. Now, unfortunately, whenever you create a new variable, it sticks it in the last column. Okay, it adds it, it appends it to the data set as the last column. So you're often not going to see it. So from there, you might have to combine it with select. So here we're going to take Star Wars, we're going to mutate, and that adds it to the last column. And from there, we're going to select the column's height and height in inches, and we're going to take the first row. And here we get Luke Skywalker, 172 centimeters or 67.7 inches. Okay. When you use mutate and you it's going to add a new column to the data set. One thing you need to do when you use mutate is it needs to be a function that's going to create just as many values as there are rows, right? So if you have 87 rows in your data set, whatever function that you're doing with mutate needs to create basically a vector of 87 values, right? So height divided by 2.54, if I have 87 height values and I divide by 2.54, I'm going to get 87 values, okay? But if I were to use a function like mean, right, and I put in 87 values into the function mean, it's only going to produce 1 value, right? So using a function like mean is not going to work. So there are other functions which we call window functions or something like that, which so something like the cumulative mean could work because this is going to create a vector of 87 values. So the cumulative mean says take, with one number, what's the mean of your one number so far? 77. If you do 77 and 75, what's the kind of cumulative mean of those 2 values? That's going to be 76. 77, 75, and 32, what's the mean of those 3 values? The mean of those 3 values is 61.3. If you add in 136, what's the mean of those 4 values? The mean becomes 80, and so on and so forth. And so now we're going to have a vector of 87 values, and we have no problem appending a column of 87 values. Okay, so when you use mutate, you have to make sure that whatever new column you're adding, cumulative mean or whatever it is going to have an entire vector that has the same length as the number of observations you have. So these are useful functions that get used for mutate. So things like element-wise min and max, okay? So min and max would normally just produce, you give it a vector and it just produces one value, right? But you have element-wise min and max, you have cumulative min and max, you have cumulative sum and product. You can have between, which will give you true, false. You can have the cumulative mean, you can add lead, lag, and you can have entile, okay? So here's just a few examples of how some of these things work, okay? So the cumulative min for the mass is just going to be like, what's the smallest value we've seen so far? So the first value is 77. That's the smallest value. The next value is 75. That's even smaller. The next value we see is 32. And after that, is there any value that's smaller than 32? No, 32 is the smallest value we've seen so far. So the cumulative minimum mass becomes 32 down here. Okay. Ratio is mass divided by the mean of the mass. Okay, and so we can say, all right, it calculates the mean of the mass, and then it just says, you know, are we greater or less, you know, heavier or lighter than the mean of the mass? So it looks like the mean of the mass, I don't know what it is, but it's probably something around 100, maybe a little bit less than 100, like 98 or something, okay? So 77 divided by 98 or whatever is 0.791, 75 divided by whatever it is, 0.771, and so on and so forth, okay? Mass year P min is going to take the column mass and year, and it just says which element is smaller, the person's mass or the year they were born, right? So P min is element-wise minimum, and it just says, okay, take these two numbers and what's the smallest? Between 77 and 19, the smaller value is 19. Between 75 and 112, the smaller value is 75. Between 32 and 33, the smaller value is 32. Okay, so that's element-wise minimum, right? So it's you give multiple columns, and it says of those columns you've provided, which value is the smallest. All right, and then lag, here I'm saying lag of mass year P min, and basically it says just copy these values, but shift them down too. That's what lag does, okay? It offsets the column by a certain number of values, okay? And the opposite of lag is lead, okay? And so lead will kind of copy them, but offset them in the opposite direction. All right, any questions on any of these mutate examples or functions or things like that? So if you have an idea of like what kind of things that you're capable of with mutate, you know, you can often do a lot of stuff, okay? All right, so now let's talk about summarize. So summarize is probably the most valuable or useful feature in dplyr, and that is where you take multiple of vector values and you summarize it down to one, right? So things like, let's calculate the mean, right? You take multiple values and you get the mean, which summarize it down to one. Let's calculate the standard deviation or the variance. Multiple values get summarized down to one, okay? So here I'm going to select the columns height and mass, and from there we're going to create several new columns. We're going to take the average height, the variance of the height, average mass, and then I'll also get the minimum height, the maximum mass, and the count. All of these things are summary values. I'm going to have them ignore anything that's missing. So na.rm is equal to true for all of these things. And so we get the average height, the variance of the height, the average mass, the minimum height, the maximum mass, and the count. These are all examples of summary functions that take multiple things and summarize it down to just one value. Okay. So when we so we do that, and this does it for the entire data set, of which we have, I think, 87 observations. And so the average height for all 87 observations is 174. The average mass of all 87 observations is 97.3, et cetera, et cetera. We have 87 observations, which is used with count n. We can also combine the summary functions with groups, okay? So group by what we're going to do is we're going to take our data sets and we're going to group them by species. Okay, and so we have species like humans and droids, and there's different alien species. And so we're going to group our characters by species. Now, if you just apply group by, it doesn't look like much happens except this little notation appears. It says groups. There's 38 groups for the different species. Okay. And what I can do now is I can combine group by with summarize. And this is probably the most useful and powerful function in dplyr, is the combination of group by and summarize. Okay, we're going to group by the species. We're going to select these columns, and then we're going to summarize. We're going to ask for the mean height, the standard deviation of height, the mean mass, and the standard deviation of the mass. And so what we have is we had one member of the Alina species, one member of the Basilisk species, and one member of the Syrian species. And we can see that in the counts. And so the height, the mean height is 79 and the mean mass is 15. And when you only have one observation, there's no standard deviation. Okay, we had 6 droids in our data set. The mean height of our droids is 131. The standard deviation in height is 49.1. The mean mass is 69.8, and the standard deviation in mass is 51. And that's what we have here. Okay, now you might say, well, can we just get only the rows where we have more than one count? Okay, yeah. Okay, we can take this output, which has 38 rows because we have 30, right? So we're getting one row for each group now. We have 38 species groups. So we're getting one row for each group. So I have 38 rows, 6 columns. And from there, I can say, you know what? Filter it to only groups where the count is greater than 1. Okay. And so now we have 6 species. Okay. We have 6 groups and 6 columns. And we're going to arrange them in descending count. All right. So we have 35 humans. The mean height is 177 with a standard deviation of 12.5. And the mean mass is 82.8 and the standard deviation is 19.4. As far as droids go, the mean height is 131. We have 4 people who had 4 characters with no species. Their mean height is 181. We have 3 characters who are Gungans, and their mean height is 209. And 2 characters that are Kaminoan and Mirialan. I don't know what these are, but here we go. Okay. Oh, actually, we might have had more than 6. Here I've said head, which limits it to the top 6 entries here. All right. And so there we have that. Okay. Is this okay using the group by and the summarize? This is an important thing that we can do with dplyr. And so I think you've got a few exercises in your homework that will have you use group by and these dplyr functions. And I strongly recommend them. Okay. You can also use group by in combination with mutate. Okay. And so, for example, you might want to find the z-scores, right? Z-scores is the difference between the mean but expressed in standard deviations. And you can have this apply to species. So we can say, compared to other humans, not the entire data set, compared to other humans, how does Luke's height compare, right? And so Luke's height is he's 3.37 standard deviations below the mean for humans, right? Darth Vader is 2 standard deviations above the mean for all humans and things like that. Okay. Whereas if we're looking at something like C3PO is shorter than Luke, right? His height is 167, which is shorter than Luke, but compared to other droids, he's well above the mean height, right? So here we're calculating values based on the group, right? The z-score compared to their group, not to the entire data set. So you can combine group by with mutate. Okay. And if you did it without group by, then so here I just comment out that line group by, and now it's just being done to the mean of the entire group, right? So Luke Skywalker is taller than C3PO, so he has a positive z-score, whereas C3PO is below the mean, so now he has a negative z-score. You can use group by multiple times. So here's a toy data set. And this is just some made up data here, where we have three countries, Afghanistan, Brazil, China. And we have 2 years, 1999 and the year 2000. And we have 2 sexes represented here, female, male, female, male. And we have some number of cases. And so we can group by country and year. And so if we say, well, how many unique combinations of country and year are there? We would have a total of 6. We have Afghanistan 99, Afghanistan 2000, Brazil 99, Brazil 2000, China 99, China 2000. And we can say, you know, give me the sum of the cases, and it just kind of adds up the numbers here. Okay. Now, what I can do here is I can further summarize, and I can say summarize here. And here, the groups, we have here, we created 6 groups, country and year. And within those, there remains 3 groups. We have the country groups, Afghanistan, Brazil, China. So I can apply summarize to this output. Okay. And now we get three rows, Afghanistan, Brazil, China. And I can apply summarize there, and it will just give me the sum of those things, right? 4, 8, and 12 added together gives me 24. All right. If we change the order of the grouping, if I said group by year, then country, then we get all of the 1999 together and all of 2000 together. And now we have 2 groups, right? So we're kind of creating a hierarchy of groups. So we're going to say we've got, and then if I applied summarize to here, then I would only get 2 rows, a row for 1999 and a row for 2000. And then if I apply summarize here again, I get the same result, a total of 24, right? So you can kind of create a hierarchy of groups by putting in multiple values inside the group by. So you can group by one column, or you can group by multiple columns and kind of create a hierarchy of groups. In the interest of time, I'm going to skip over this section, the 2 table verbs. Okay, I'm going to skip over this, and I will not put 2 table verbs on the midterm exam. Okay, so this 2 table verb section, you can look over it on your own time. I'm going to kind of skip over it. So we will do that. Okay, no 2 table verbs on the midterm. And now we're going to get into characters and working with characters in R. Okay, so we've got characters, we've got strings in R, and you just say, you know, you got quote marks, and you can ask type of, and these are basically characters. I think we're familiar with that. Okay, when you, to create a character, you just use quotes, and if you got quote, double quotes and single quotes, you can kind of mix them and things like that. If you try to combine double quotes and single quotes, you know, or if you try to use double quotes within double quotes, you know, it produces all kinds of stuff, right? So you are able to escape double quotes using a backslash if you need to. Okay. All right. The function character will create a character vector of a specified length, and if you just give it a number to say, you know, give me a character vector of length 5, it's going to create empty characters. Okay, a vector of empty characters, which basically what we have here. Okay, this empty character, okay, this empty character is not the same as character 0. Okay, character 0 is a character vector of length 0, whereas if you put in, if you said, give me 1 empty character, that would be the equivalent of character 1, right? So this is a length 1 character vector. This is a length 5 character vector. Okay, character 0 is a character vector, but there's of length 0. So there's not even an empty character. It's just a length 0 character vector. Okay. The paste function also allows you to build strings by kind of pasting multiple character strings together, right? So it's going to, the inputs for a paste function are going to be our objects, and then it converts them into character, and then it kind of pastes them together to kind of form strings, right? And you have a couple options. You have separator and you have collapse, right? The default is in paste, the separator is the space, where paste 0, the separator would be the empty character, okay? So let me just show you some examples, right? So you can say, I ate some pie and it was delicious, and it will paste it together, and he gets, I ate some, and it turns pi, which is this floating point value, converts it into a character. I ate some 3.14159, blah, 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 and it was delicious, right? Okay, here I've got multiple characters, bears, beats, Battlestar Galactica. These are multiple strings here, and we're going to paste them together using the separator comma space. And so this produces this one string, bears, beats, Battlestar Galactica. Okay, okay. Here I'm going to paste H, the character H, with this vector of characters A, E, and I. And this produces a vector of length 3 with the characters, with the strings ha, he, and hi. Okay, this is a length 3 vector. Okay. Similarly, I can paste ABC, a vector ABC, with the vector 1, 2, 3, and it pastes them element wise. The separator here is there's no separator. Okay, empty string. So I get A1, B2, C3. This is a length 3 vector. Okay, here, if I use the argument collapse, and I basically have, I'm going to combine A, 1, 2, 3, no separator, and I'm collapsing them. Then it takes basically the output, which would have been A1, A2, A3, and it collapses them, okay, into one character string. Right? Does that make sense? The difference there between collapse and not using collapse. This collapses the output. Here I have three strings because I didn't use collapse, whereas here I used collapse, so it produces just one string. All right, we have print functions. We got print, you have cat, and then if you need to format stuff, you can use format. And so most of the time when you print out a character, it puts little quotes around it, and you can disable that. You can use print with quote equals false, and it will remove the quotes there. You can also use no quote, and no quote produces a no quote class object, which will always kind of print this out without the quote marks from here on out, okay? Cat will basically concatenates multiple character vectors into a single character vector, right? So back here we said X is this vector, is this character vector or character string hello world. And here we are going to, cat is kind of like paste, but it's going to just kind of combine them and just output them to the screen. It doesn't produce an object like paste does, but it just combines them and outputs it to the screen. So if I say cat hello world along with hello universe with the separator comma space, it says hello world, hello universe, and it just outputs it to the screen. Okay, it's a little bit different from no quote. One thing you'll notice is that when you use cat, you don't get the square bracket 1. Square bracket 1 is kind of the output that you get when you have a vector output, and here you don't have that. Okay, you don't have the vector index. Okay, and it doesn't produce an object, right? It returns a null, meaning that, if you take print and you assign print to something, it will assign that object somewhere, whereas cat, there's no output to be assigned somewhere. But what you can do is you can have things, when you cat things, you can have it output to a file. a text file. So you can say, you know, I want this output to a text file called hello.txt, and it will produce this file. Now you can also use the argument append, and that will not overwrite the file, but it will just add to the bottom of the file, and your file will get longer and longer every time you run it. There's other things you can look at in the help for cat, which is just concatenate things together. Okay. Format allows you to kind of do pretty printing, so you can kind of make sure that the width, and it will just kind of add space padding, or you can have it remove spaces, trim the white space, or justify, which is kind of a form of width and things like that. You can also control how many digits gets produced, or the number of digits and things like that produced in scientific notation. So here's just a few examples. Okay, so if I do 1 divided by 1 through 5, and I say digits 2, you get 1 divided by 1, which is 1, but it produces 1.00. 1 over 2 is 0.50. 1 over 3 is 0.33, 0.25, 0.20. Okay, and so this takes this, and you'll notice the output of format is going to be strings. Okay, and it says, and we're keeping 2 decimal places after the 2 places after the decimal. Here I'm going to say scientific true, and so this outputs everything into scientific notation. So 1.0 times 10 to the 0, 5.0 times 10 to the negative 1, 3.3 times 10 to the negative 1, so on and so forth. Here we can say, here are these words, hello world, hello universe, and we want the output to have a width of 10. And so every one of these strings has a width of 10. And here we said justify left, so it's going to put the text on the left-hand side. You can say justify right, and it could also place the text on the right-hand side and things like that. And it's going to just kind of add text to kind of make sure the resulting string has a width of 10. So these are just examples of format. There are some basic string manipulation functions in R, which will kind of give you things like, you know, make everything lowercase, make everything uppercase, translate the characters, which is kind of a weird function that we probably don't use that much, but you can also extract substrings, and you can split the strings and things like that. So here's just a few examples. One, we can count the number of characters, hello world, hello universe. Those all have 5 letters each, except for universe, which has 8. You can convert everything to lowercase. You can convert everything into uppercase. You can replace. This is character translate. And basically it just says every instance of the letter capital H replaced with the letter Y. And so now you get yellow world, yellow universe. Here you can, you know, replace all instances of E with the number 3, instances of L with the number 1, I with the exclamation point, and O with a 0. And now it feels like, I don't know what this feels like, but this is still says hello world, hello universe, but just written all kind of funny here, right? This might be like what some TV show shows for if you're trying to enter the hacker world and communicate with hackers or something. This is what the TV show might show, or something like that. Okay. Substring just says, you know, starting at the 2nd character, give me the next, and ending at the 9th character, give me what we have here. Okay, so starting at the 2nd character, ending at the 9th character, that's what we get. Here we can say take the string hello world and split at the space. And so now it produces 2 strings, hello and world. Okay, here we can also say split at the O. And so hello world, we get hell, and then space W, and then RLD, right? It's splitting the string at the letter O. All right, and now I'm going to introduce stringer. And this is very exciting. Before I do that, let me go ahead and give you your second view quiz answer for the day. Today's second view quiz answer is the letter A as in apple, A as in apple, okay? All right, have you guys worked with regular expressions before? Has anyone worked with regular expressions? Maybe some of you, okay, some of you shaking your head, some of you nodding your heads. Okay, regular expressions I think are like the coolest thing. And if you invest time learning regular expressions, you can do a lot of stuff, okay? So Stringer is R has a way to work with regular expressions, but Stringer kind of unifies this. It's part of the tidyverse, and it makes working with regular expressions in R like a beautiful thing. Okay, so yeah, I'll just say, if you're going to use regular expressions in R, highly recommend always using the Stringer package. And oh, I'm sorry, this got all messed up. This should be a bulleted list, and it's not. What happened here? Okay, but you got string concatenation. String, it will return the number of characters in the string. String sub, which will produce a substring. String dupe, which will duplicate characters. String trim will remove leading and trailing white space. String pad will pad a string. String wrap wraps a string into kind of a paragraph if you need to. And I have string trim listed here twice. Okay, I don't know what I did on this slide. I messed it up. But there's some good documentation here about Stringer. Recommend those when you do try things out. All right, so here is paste and string concatenate, which are pretty much similar things. Okay, the difference being, notice what string concatenate does when it enters handles null and zero length vectors. So here I say, paste X, which contains the string hello world, and null and character 0 and hello universe, that. And if you do paste, it treats these null and character 0 as zero length things, but it inserts them, and you get hello world, comma, space, hello universe. Whereas string C will intelligently say, let's ignore these things, and just gives you hello world, hello universe. Okay. So we've got that. Okay. String length will work with factors. Okay. So if you just do number of characters and you do something with a factor, it says, I can't do that. Whereas if you do it with string length, it works. So if you do factors on the month.names, which will be January, February, March, April, and so on and so forth, it works. And so January has 7, February has 8 characters, March and April have 5, May has 3 characters, June, July, August, September, October, November, December, right? Shortest name is May, longest is September. I don't know if you guys knew that trivia for the things here. Okay, so those are your basic functions, but really the exciting part really comes down to the regular expressions. And so here, let's talk about regular expressions. So with regular expressions, we have kind of this language for identifying patterns, writing patterns to match kind of different strings that fit a certain pattern. Okay. And you have certain symbols and they mean different things. And I think the best way to do this is just show you a bunch of examples and hope it starts working here, right? And so these are some applications of regular expressions, right? So you can see if a phone number has the correct number of digits, so that's a simple one. You can see if a date follows a certain format. You can see if an email address is a valid format. Now this email addresses have gotten really, really complicated just because now you have all sorts of crazy domains, right? It used to just be like you have .com, .net, .edu and things like that. But now you have all kinds of domains, right? Like .info, .me, .whatever, right? There's all sorts of things. So email address, this is no longer a really useful thing. For email addresses, you kind of just have to accept everything. You just have to say like, is there an @ symbol somewhere in there? And if so, then it's probably some kind of email address. But I mean, if even it's something as simple as that, right? Like, is there an @ symbol in there? That could work, right? Oh, and this is always annoying, right? You go on the website and it says your password needs to have this many characters and this many capital letters and this many numbers and this many special symbols, and it can't contain your own name and stuff like that. But you can do that's powered by a regular expression. That part of the website that's annoying is powered by a regular expression. You can search for things like this, and you can see, sometimes people go with nicknames, and you got Will, Bill, W, William, things like that, and you can search for a document that finds all occurrences of these types of things, right? So when you do this, you have string detect, and that will say, if it finds the pattern in the string, it will return true, and if it doesn't, it returns false, okay? You can also have string locate, which will say, I found it, and it's located at this position. You can do string extract, and it's going to say, I found the pattern, and the string that matches the pattern is this, okay? And in the pattern, with patterns, there's something that we can create called capture groups, which I will explain. And you can also do string match to kind of pull out the capture groups kind of separately and handle them, okay? And you can also split the string and return them. And you can also say, maybe we're looking for multiple instances. And so all of these things will have a string detect all, string locate all, string extract all, and so on and so forth. And so, so let's do this. Okay, so your most basic pattern that you can do is just going to be literal characters. And this is basically using the find function. And I think probably you've written some kind of essay on, Microsoft Word or some word processor. And at some point you had to do like a find and replace, right? You find in your document and you say, find all instances of this thing and replace it with something else. You decide to change the name of your character, or you change something else, right? And that is basically doing a literal character search. You're finding a certain string, and like Word will have a basic option, do I need to match cases and things like that. But you're basically doing a literal character search there, okay? So you can say, I want to find things where you have the letter R or the number or something like that, right? So here we're going to say, the string that we're searching is going to say, I love stats. And this thing that we're searching could be like a much longer document or paragraph. And the pattern that we are going to search for is going to be the literal string STAT. And it's going to say, oh, I found a match right here. And it starts at character position 1, 2, 3, 4, 5, 6, 7, 8. It's going to say it starts at position 8. It ends at position 11. And there is the location of that pattern, STAT. Okay. Now, if I said, I want you to search for STAT in this string, I love stats, when you do a literal character, it's case sensitive. And so it's going to say, well, I can't find this. I can't find this. I can't find this exact character thing, lowercase STAT. That does not exist. And so it gives me an NaNA. Okay. Here, we've got, I love statistics, so I am a stats major. And we can do string locate. And here it's going to find the first instance. And it's going to find it in STAT. And so it finds it in position 8, ending at position 11. You can also do string locate all, and it's going to find all instances of this pattern, STAT. And so string locate all is going to search this thing. And it's going to say, oh, I found one match where it started at 8 and ended at position 11. I also found another match where it started at character position 30 and ends at position 33. And we have this, okay? So the output of this is going to be basically a matrix with 1 row, 2 columns, start and end column. And here we get a list, okay? A list in case, because this thing, love stats, could be a vector of multiple strings. And for every entry in that vector, it would produce its own matrix. Okay, so it would be a list of matrices. Is that okay as far as how this function works? Let's take a look at meta characters. This is what really makes regular expressions much more powerful. So rather than just limiting ourselves only to these literal string character patterns, we can now make things more powerful with the meta characters. And these are the meta characters that appear in regular expressions. And this is really what powers everything. And every single one of these characters does something special. Okay, this is like the superhero team for regular expressions. Okay, so the dot, this little period here, the dot is the wild character. Okay, it's going to match any string. I'm sorry, any character. It's going to match spaces. It's going to match letters. It's going to match numbers. It's going to match symbols. It's going to match everything except a new line. So it's going to go anything in the line except a new line. Okay, so I've got here I've got a vector of strings. Okay, a vector not, note, not, KNOT and NUT, and it says, do you detect any character T, any character T? And it's going to go through all 4 of these things and it says, yes, I found it. I found it here, I found it here, I found it here, I found it here. True, 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 true. And it gives us a vector, right? Here we're going to say, okay, what about this? NO wildcard, okay? NO wildcard. So here it says, do you detect it? And it's going to say, yes, I found it here. NO wildcard, NO wildcard, NO wildcard. Uh-oh, not here, false. Okay, and you, there's nothing here. Okay. All right, so here I've got 5.00, 5100, 5-00, 5 space 00. And if I say detect 5.00, what will this return? Yeah, where is it? Okay, yeah, it's going to return true, 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 true. it's gonna match all of those things. Okay, so the answer is over on this slide. True, 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 true. Okay, now let's say you want to say let's say you actually want to work with the period, the literal the literal dot, right? If you want to do that, you have to escape. You have to escape the meta character using a backslash. Okay. However, in R, the backslash itself is a meta character for normal strings, so we need to double backslash it. Okay. And so so here's an example. Here I've got this string ABC square bracket DEF, and let's say I wanted to match this square bracket, right? If I try to create a pattern with a square bracket, this regular expression is going to say, oh, that's a meta character, that's a special character, and it's going to fail, right? If I want to match this the literal meta character, I have to escape it with a double backslash. Okay, here I get this error, right? Error, missing closing bracket on a bracket expression. Okay, you regex missing closing bracket. Okay, that's the error I get. And that basically means you're trying to work with a bracket and it's not closing. So here, if you want to say, I want to match the actual square bracket, you have to escape it with a double backslash. All right, so going back to here, we had this thing and we said, I want to look for 5.00, and this is the meta character. So it's going to find it here, 5, any character 005, any character 005, any character 005, any character 00, and we get true, 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 matches all of those. Now, if we want to match only with the literal dot, and if I do 5 // dot, this will only match 5 literal dot 0.00, and that will only match this one, true, false for everything else, false, false, false. Okay, so what about this? All right, here I've got a character set. So the square bracket establishes a character set, and it will match one and only one of any of these characters. Okay, so here I've got a vector, pan, pen, pin, P0N, P dot N, PAUN, PWN, 3D, and happiness, HAPPINESS. Okay, And here we want to see, does it match this string? P, one of the characters A, E, I, O, U, followed by an N. Okay, so basically we need P and one of the characters. So pan, yes. Pen, yes. Pin, yes. P0N, no. P dot N, no. Okay, PAUN, no. We've got two characters here. Okay, this is only gonna, it's just one character in this thing. Okay, PWN, E3D, no. Okay, it needs to be one of the A, E, I, O, or U. What about happiness? Yes, okay, because I have a PIN right here in the middle of happiness. Okay, so when we run this, we get true, pan is true, pen is true, pin is true, P0N false, P.N false, PAUN false, PWN false, happiness, PIN over here true. Okay, so it's P, one of the characters A, E, I, O, U, and N. Okay, does that make sense as far as the square bracket character set, one of the characters in here? Okay, so if you want to match all of the capital letters in English, we could define the character set A, B, C, D, E, F, G, all the way up through Z. Okay, now this is inconvenient to have to do, so we can establish a range of characters, right? So you can just do capital A dash capital Z, and that will match all of the capital letters. So you could do A dash Q, and that will do all the letters A through Q. A dash capital Q, and that will do all uppercase letters A through Q. You can do A dash Z, capital A dash Z, and that's going to do all 52 ASCII letters. So A through Z, uppercase, A through Z, lowercase. Okay. And 0-7 for all digits 0 through 7. Okay. Now, regular expressions are very, very, very ASCII centric. Okay. And I recognize that, you know, if you're from a European country, you know, there's a lot of, you know, a lot of languages have accents and things like that, you know, and if you're from, you know, in any country that doesn't use the Latin alphabet, right, like Russia or, you know, any, you know, a lot of Asian countries don't use the Latin alphabet. This is not like the ideal thing. Now, there have been efforts to kind of expand regular expressions for, you know, other languages and stuff. But as it stands, regular expressions are still very, very, very much ASCII centric, meaning it's really designed just for kind of the 52 capital lowercase, you know, and you know the ASCII set of characters and symbols that we have. Okay. Okay, so here we have, so let's take a look at some character ranges here, right? So character ranges are useful to kind of match various occurrences of a certain type of character. So let's look at this vector. We've got 1, 2, 3, ABC, lowercase ABC capital, smiley face, AB 1, 2, A 8908 AB. Okay, and what if we want to match 3 adjacent digits? Okay, adjacent digits like 1, 2, 3, or 4, 5, 6, or 3 digits next to each other. What kind of pattern can we write there? Digits. So digits will be 0 through 9. So one pattern that we can write is going to say, you know, I want to match character set 0 through 9, character set 0 through 9, character set 0 through 9. Okay, and that's going to be 3 digits. This is any digit 0 through 9, any digit 0 through 9, any digit 0 through 9. And so this will return true here, false, false, false. We don't get a match here. This is false because I only have 2 digits, and we get a true here. I got 4 digits in a row, and that will satisfy, you know, do we have 3 adjacent digits? And it will match. It reads left to right. It's going to match the 890. Okay, so we get a true there. Okay. And if we did A through Z, A through Z, A through Z, we'd get 3 adjacent lowercase letters. Sometimes you want to work with a negative character set, meaning, so it's like kind of a character set that we have here, but you just want, you don't want certain letters, right? You don't want certain letters. So that's going to be a negative character set. So this will be basically by matching any character that is not part of the set, right? And so you're going to put the caret, the meta character, inside the square bracket to establish a negative character set, okay? So for example, if we do square bracket caret A-E-I-O-U, that says I don't want these letters, A-E-I-O-U, right? So it says any character but A-E-I-O-U, any character but A-E-I-O-U. Now, one important thing is that this caret, this meta character, it's got multiple meanings depending on where it appears in the regular expression. This is probably one of the most tricky meta characters to deal with just because it has multiple meanings. But if you put it inside the square bracket at the start of the square bracket, it says, I don't want one of these letters, right? So here, if I say, I don't want capital A through Z, all right, what's it going to match? It will match the number 1. It will match lowercase a. It will give me a false here, okay? Because we don't want that. It'll match this, it'll match this, it'll match this. So it'll give me true on everything except for the capital letter A. Okay, now, if you don't put the caret as the first character inside the square bracket, then it becomes the literal caret, okay? So here it says, this just means I want a capital letter between A through Z or the caret character, okay? So now this is a regular character set where it says I want A through Z or the literal caret character. So now we're going to get false on everything. We're going to get a true for the capital A, and we're going to get true for the caret. True for the caret. Okay. All right. So here's a question. What would I write if I want to say I want to match anything except for the literal caret? Okay. So one way we could do this is we could do a negative character set, caret that says I don't want, and then you can put in a double slash caret here. This double slash is technically optional because if it's not the first character, then it becomes the literal thing. So if we do this, then we'll get, it matches anything except for the literal character, okay? And we have that. Okay, and basically, anytime you put in a meta character into a character set, it basically becomes the literal version of itself. So the dot here inside the character set is just the literal dot. So here, this is AE literal dot IOU. So here we're going to match basically everything. So we will get a match on pan, a match on pen, a match on pin, not on P0N, because this dot is not a wildcard character. It's now just the literal dot. We will get a match on P.N, because the dot is one of these things. We don't get a match on PAUN, and we don't get a match here. Okay. So you putting a meta character inside a character set, other than the dash, because the dash still defines a range inside the character set, will be the kind of the literal character there, right? So the dot inside the character set now represents the literal dot character rather than the wildcard character, right? So the only exceptions to this rule is the brackets themselves, the dash, and the caret if it's at the front, and then the backslash. Okay, I know it's complicated. It's a lot of stuff. It's a lot of stuff. All right. We have character classes, which are basically shortcuts for defining some of these character ranges, right? So here you can do /d, little d, /little d is the same as writing this. And /big D says I don't want that, right? So lowercase means you do want the thing, and capital letter says you don't want the thing. So D is any digit, capital D is non-digit. W is a word character. So word character is the lowercase letters A through Z, capitals A through Z, numbers 0 through 9, and the underscore. Okay, so it's kind of like if you were to like write a username. So when you think of like what can you put in for like an email address? I guess email addresses you can put dots in there, but generally, like if you say like come up with something to use for like a username for a website or something, generally what they're using is your username has to be basically word characters. So lowercase letters, capital letters, the numbers 0 through 9, and underscores. And then capital W is anything that's not that, non-word characters. Okay. S is a white space character. White space character is basically spaces, tabs, things like that. And these are all like different versions of white space characters. New line, carriage return, tabs. I don't know. These are like weird things that appear. Okay. And so these are pretty much equivalent of these things. These are just like shortcuts for creating kind of these character classes. Okay. So as far as white space characters go, you have the form feed, the line feed. So form feed is a page break, line feed is a new line, R is a carriage return, /T is a tab, and /V is a vertical tab. This is it's a little bit strange. Like the idea is, I don't know if you've like seen an old typewriter where it's like you go chug, 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 you're typing, and then there's like this little roll and it like slides across, and then it hits the end, it goes ding, and then you see the person and they slide it back, right? So so that is, so when they hit the end of a new line, so there's two things going on there, right? So we're accustomed to like writing this on a word processor. We reach the end of the line and it automatically the cursor moves down to the next line. That includes two things: the new line, which is basically rolling the roll up, so the paper moves up like a 1/4 inch so you can get to the new line, and then you have to like slide the after you hit the ding and you slide the whole roll, that's the carriage return. So on computers there's a new line, carriage return combined every time you hit enter, because it's imagining, they're basically translating from like a typewriter into like a word processor thing. Okay. It's like nobody really pays attention to this stuff, so everybody just says, all right, any kind of white space character, I don't even know what a vertical tab is, but white space character /S is going to be what we've got. Okay. So this here says I want the pattern, the letter P followed by any digit. Okay, so what are we going to get? We're only going to get a match on P0N. Everything else will be false, right? So we get false, 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 true on P0N, false, false, false for everything else. This says I want P followed by anything that is not a digit. P followed by anything not a digit, okay? And so we're basically going to get the inverse of this thing. We get true, 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 false on P0N, and true, true, true. We got P's followed by anything other than a digit. All right, here, P followed by anything that is not a word character. Not a word character is, so word characters are letters and numbers. So what would, and underscores. So what would it match? So anything that's not a word character. So this is P followed by a letter, number. So these are all word characters. So we're going to get falses on these because it says I don't want a word character. P dot, this will match. This will become true. This will not match because that's a word character. This will not match because that's a word character. Okay, so we're going to get false on everything. We only get true on the P dot. This is not a word character. A dot is not a word character. There is, you also have what's known as Posix character classes. This is like appears on like Unix systems and stuff like that. So if you, so we have like the /D and the /W. There's other ways. So you pretty much have the same thing. You got alpha digit, alpha numeric, which is this. So alpha numeric is similar to word /w, except it doesn't include the underscores, right? And you got space. And then you also have punctuations, printables, printable characters excluding the space and things like that. Okay, and control characters. These are supported in R and supported on Posix systems. So here you can say, I want anything that has a letter, that's going to be true. Anything that has a digit, so it's only going to be true for this one, P0, and the 3 here. So you'll get trues on there and then false for everything else, right? So you can do it like this. And again, you give it a second, you have to kind of do double score brackets here, okay? We have anchors. Anchors basically tell the regex engine to search for the pattern, but only in certain positions. So you can say, I want you to search for the pattern only if it's at the beginning of the string, or only if it's at the end of a string, or more complicated, you can say, I want it only at a word boundary, or places that aren't word boundaries, things like that. So let me just kind of show you. So here, the caret makes another appearance. If you put the caret not inside a character set, but just at the start of a string or something, this will mean I want it at the start of the string. You can also do a /a to say I want this at the start of the string. You can do $sign to say I want it at the end of the string, or /z to say I want it at the end of the string. So let me just show you a few examples here. Okay. So here I've got a character string. This is just a length 1 vector, right? So this is just important to remember that back here, this is like a length 1, 2, 3, 4, 5, 6, 7. I've got a length 7 vector. And here I just have a length 1 vector, but it's a long string. And the string is the quick brown fox jumps over the lazy dog. And that's not a mistake that I have the dog written there twice, okay? So here we're gonna say, replace any instance of the text THE with a dash, and it's going to go through and it's going to search for the pattern THE, and it replaces it with a dash. Okay, so I get dash quick brown fox jumps over dash lazy dog. I'm going to change the pattern that we want to match, the THE, to a caret THE. Caret THE says, only search at the start of a string, only search at the start of the string. So therefore, it's only going to match the start, the THE at the start of the string. And this THE over here does no longer matches because it's not at the start of the string. So here we get dash quick brown fox, and it only replaces that one. Same thing, I can also do /a. And again, in R, you have to do the double backslash. So double backslash capital A says, I only want the start of the string, THE. In my opinion, this is harder to read than the caret THE. So, generally I use the caret, but this is just as valid, okay? And this will only match the first instance of THE. Okay? And here you have THE followed by a $sign, which says, I only want you to replace it if there's a THE at the end of the string. And here, there is no match. There's no match for THE at the end of the string. The last part of the string is dog. And so there's nothing to replace. Nothing gets replaced with a dash. Okay, here's a couple more examples. Here we say replace dog, D-O-G, anywhere with a dash. And so we get the lazy dash. Okay, and here dog $sign says only do it if it's at the end, dog $sign. So it only replaces the last instance of dog. All right, /b. This is a word boundary. Here it says replace anything with a word boundary with a dash. Okay, word boundaries exist at the start and the end of a word. Okay, and you think, well, isn't that just the space? And it's different. It's not the space character. The space character kind of establishes word boundaries, but you have a word boundary at the start of the word W, and you have it after S. And so there's a word boundary between the quote mark and the W. You have a word boundary between the S and the space. You also have a word boundary between the space and the J, okay? So word boundaries aren't actual characters, but they are locations that exist at the start and the end of each word. So they don't have characters. They aren't characters themselves, but they are there, okay? And so we're just kind of having the word boundaries appear using the dash, right? So there's a word boundary between the space and the J. There's a word boundary between the S and the space. Do you see that? And so so every word has two word boundaries at the start and at the end of the word. And so here, this kind of shows where the word boundaries exist. All right. And if we say, okay, what about non-word boundaries? Okay, so every word, okay, or all, these characters have non-word boundaries between every character, every letter. So there's a non-word boundary between the W and the O, between the O and the R, between the R and the D, and between the D and the S. There are non-word boundaries between the inner characters of any word here. Okay, there's so the result is going to be here, right? You got not a non-word boundary between the W and the O, between the O and the R and the D, and the D and the S. Right? Does that make sense for where the word boundaries exist and where the non-word boundaries exist? Okay, and then so we're not adding anything between the S and the space or the space and the J, because those are the word boundaries. So replacing any word boundary with dashes, or non-word boundaries with dashes here. Okay, so what does this look like? All right, so here it says what we want to do is we want to find the pattern word boundary, //b is word boundary, and the letter UMP, the letters UMP, okay? So this basically says I only want to replace the character string UMP with a dash if the UMP appears at a word boundary. So basically, if it's only at the start of the word, okay? So I've got words jump, jumping, umpire, pump, umpteenth, and lumps, and it's only going to do it for the UMP that appears if the U is preceded by a word boundary. So it's going to be umpire and umpteenth, and the other instances of UMP will not get replaced. Okay, so the UMP and umpire and UMP and umpteenth will get replaced, because this says I want to find a word boundary followed by UMP. Okay, here it says I only want a UMP if it's not preceded by a word boundary. Okay, so where are we going to? So question, you can either just nod or shake your head. Jump, will we replace the UMP here? Yes. Jumping. Yes, this is not a word boundary, right? There's a non-word boundary between the J and the U, so that will work. What about umpire? No, okay, because the umpire, the U here is preceded by a word boundary. Pump? Pump is a yes, because the U is preceded by a non-word boundary, okay? Umpteenth, no, because this is word boundary. Lumps. Yes, there is a non-word boundary between the L and the U, okay? So we're going to get the words, the jump, jumping, pump, and lumps. Those UMPs will get replaced with dashes, whereas umpire and umpteenth remain untouched. Okay, what about ump//b? This says ump with a word boundary. This means we only want ump at the end of a word. So we're going to get jump and pump. Okay, jump and pump, because we're saying we want UMP and it has to be followed by a word boundary. So basically it has to be at the end of the word. Okay, and UMP followed by a non-word boundary. So we want UMP only if it's not at the end of the word. So we'll get the UMP in jumping, umpire, umpteenth, and lumps, because those are not at the end of the words. So we get jumping, umpire, umpteenth, and lumps. All right, so this is quite powerful stuff. searching for things that either are at word boundaries or non-word boundaries. I gotta speed things up. It's 5:41. Okay. Okay, what's the difference between caret dash 0 through 9, caret square bracket, caret 0 to 9, and 0, 9, caret? Okay, so caret outside of a thing is an anchor, so it says it must be at the start of the string. Start of the string has to begin with a digit. Caret inside a square bracket says we don't want, those are negative character strings. So basically it says we want things that are not digits. And 0, 9, caret, the caret inside the thing, but at the end is a literal thing. So we want a digit or a caret here, okay? I'm going through this quickly. You can read through this slide, but hopefully it will make sense. All right, quantifiers. This makes things exciting. We can find a thing and we can ask for 0 or more of those things, 1 or more of those things with a plus. Question mark means 0 or 1 of those things, meaning like we could find it or not. Or we could use curly braces to say we want exactly this number, 3, 3 or more, or 3, 4, or 5, or some range of those things. Okay. So here it says replace any white space with a dash, and we get this. Okay. Here we're going to replace anything but white space with a dash. Anything that's not white space with a dash. Okay. And so we get kind of the opposite. We just get it looks like a whole bunch of lines here. Okay. Everything that's not a space gets replaced with a dash. Okay. Now this says replace any more or 1 or more consecutive non-white space characters with a single dash. So what this is going to do is it's going to say, all right, here is WORDS. That's a bunch of non-white space characters. And it's going to replace that entire thing with a single dash because it's saying match 1 or more. And it's greedy. It's going to try to match as many as it can. And so it replaces this entire thing with a dash. It replaces OR with a dash. It replaces numbers with a dash. It replaces 9,876 with a dash. And basically every single one of these things, 1, 2, 3, 4, 5, 6, 7, 8, all 8 of these things get replaced with a single dash. And so now I have, you know, dash space, dash space, dash space, 8 of these things. This says replace 1 or more word characters with a dash. What's going to be the difference between the output of this and the output of this? So this is non-white space characters. And this says word characters. What's the only thing that here is not a word character? That's going to be this comma, okay? So the comma here is not a word character. So the comma will make an appearance down here. And so the only difference really between this, the output of this and this is that this 9,876 becomes 9 dash comma dash. And everything else kind of remains the same. 1 or more word characters get replaced with a dash. Okay, here we say replace any digit with a dash. And so we get dash, comma, dash, 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 combo, dash, 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 password, underscore, dash, 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 dash. Okay, and here we say replace non-digits with a dash, and we get dash, 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 dash. And then only the digits appear here. All right, and let's use some quantifiers here. So this says replace 1 or more digits with a dash. So compare it to this, and basically anytime we see consecutive dashes, they will just get replaced with one dash, multiple of those things. And here, any 1 or more non-space, non-digits. So anytime we see consecutive dashes, they'll just get replaced with 1. Okay, so we get basically something. This almost looks like a phone number now. Okay, this whole thing got reduced just down to a couple dashes and some digits here. Here it says we want to replace 0 or 1 digits with a dash. Now this is going to be a little bit confusing. 0 or 1 digits with a dash. And so the result ends up being this. Here it's detecting 0 digits at basically every word boundary and non-word boundary. It says, oh, you know, there's 0 digits before the T. Let's put in a dash there. There's 0 digits between the T and the H. Let's put a dash there. There's 0 digits between the H and the E. Let's put a dash there. Okay. And here it gets, 1996, those get replaced with dashes. And the 310, here it's doing 0 or 1. And if it can do 1, it's going to do 1. And it replaces those things with dashes. Here it says we want to find 3 adjacent digits, and it reads left to right. So it's going to find 199. It's 3 adjacent digits. There's a match, and it replaces it with a dash. And then it sees the 6 here, and it goes, that doesn't match the pattern of 3 adjacent digits. So it just leaves it there. Okay. And again, it's reading left to right. So it replaces the 310. It replaces the 123. It replaces the 1, 2, 3 and 1, 2, 3, 4, but it leaves the 4 and it leaves the single digit 5 because it's reading left to right, and it looks for something that matches the pattern, 3 dashes in a row, 3 digits in a row, and it replaces it with a dash. And once that pattern match ends, it stops. Okay, 2 to 4 adjacent digits. So here we give it some flexibility, and if it can, here, when given the choice, if it can match 4, it's going to match 4. And if it can't, it'll match 3. And if it can't, it'll match 2. So here with 1996, it matches all 4. So it does that. With 310, it matches 3. Combo 1, 2, 3, it matches 3. 1, 2, 3, 4 matches that. Single digit 5 is not between 2 to 4 adjacent digits. And so it gets that. Okay. Okay, you know what I'm going to do? I'm going to keep going, all right? I'm going to give you the last view quiz answer. The last view quiz answer for today is the letter B. B as in bear. B as in bear is your last view quiz answer. I know our time is going to run out in 2 minutes here, but I do want to kind of cover these last few slides. So I'll leave it up to you. If you feel like you can just review the slides on your own and get it and absorb it that way, that's totally fine. But, I do want to kind of at least talk about it in case, I think for a lot of you, it's helpful to hear me kind of talk about these things. And I apologize that I'm going over the time here. So, but I'll just kind of go on, keep going on here. But you've got your last view quiz answer, the letter B, B as in bear. But I'll just kind of continue covering the slides. And if you need to kind of sign off and you just want to watch the video later, that's also fine. Okay. Okay, so these quantifiers, there's something known as greedy and ungreedy matching, okay? And so anytime you use kind of the star or the plus, that's going to be the greedy form. And what that means is it's going to try to find the longest possible match. And if it can find the longest possible match, it will match that and use that, okay? So here, I've got the text, Peter Piper picked a peck of pickled peppers. And here we say, I want you to find the capital P followed by any character. The dot is any character. Remember, letters, numbers, spaces, symbols, anything. It's a wildcard character. And a star says, do as many as you can. 0 through as much as you can, ending with the lowercase r, okay? So capital P, lowercase r, find everything. And what this is going to do is it's going to find the capital P here, and it's going to go all the way to this r here, and it's going to get everything else in between. So it's going to get everything from Peter Piper picked a peck of pickled pepper, and the pattern match ends there. Now, if I put in the question mark, this makes the match what we call ungreedy. Ungreedy says, don't go for the longest possible match. Find the shortest possible match that still matches the pattern. Okay, the shortest possible match that matches the pattern now is going to be capital P to Peter, R, capital P to R here, and it will extract only Peter. Okay, so that's the difference between having the question mark in here. You have to put the question mark immediately after the quantifier, either the star or the plus quantifier, right? And it's going to either go to find the longest possible match or the shortest possible match. All right, so here, if we say extract all instances of this match, okay, here it's going to pull out Peter and Piper. okay? Because Peter matches this and capital P for Piper will match that, okay? Another instance is I could say, okay, give me capital P and lowercase p followed by any character and an R. All right, so we will match Peter, we'll match Piper, and what will the next thing be that we match? We're gonna get everything from picked a peck of pickled pepper. Okay, so because the dot will match spaces, okay? So it's gonna give us Peter, Piper, and it's gonna say, all right, and again, it reads left to right. So it's saying capital P to R, match, capital P to R, match, lowercase p, all right, and we're looking for an R to finish this off. What's the shortest thing that I can do? And it starts at the lowercase p and it reads left to right and it goes picked a peck of pickled pepper. Oh, there we go, we found it, and it ends there, right? I wouldn't blame you if you thought it would match pepper, but it reads left to right and it counts the spaces as matches. Okay. If you wanted just pepper, it would be a little bit trickier to do. You could say, you know, I want only word characters, and then it won't match the spaces. It'll say, all right, picked, no, and then it'll probably, I think we can do pepper if I did this, but I'll have to try it out later, or maybe no. Okay. We have capture groups. Capture groups use parentheses. Parentheses will define what we call a capture group. And these will be things that kind of get its own separate things out. So it'll match the entire pattern, and then it will also kind of pull some of these chunks out. If you include this question mark thing, you'll get what's called a non-capture group. And it gets matched, but it won't get extracted. So I'll show you some examples here, okay? So here we get A and then parentheses B, C, D. So here it's going to match the entire pattern A, B, C, D, but the capture group is what's inside B, C. Okay. Here it says match this pattern A, B, C, but this is a non-capture group. Here it says match the pattern A, B, C, D, E, F, G, H, I. It has to match that entire pattern, and it's going to extract out the group A, B, C, and G, H, I. Grouping is useful, especially if you want to try to like match one word or the other group. So you can say MRS, this vertical line means or, MS or MR, okay, and it's going to find it in that order given. And then you can also reference any kind of capture groups after the fact using the /1 and /2 to kind of find the first or the second match groups. Okay, this is kind of complicated, so let me give you some examples. I think this will help clarify some of this stuff. Okay, so here the pattern we're going to try to match is B, C, D, E, F, G, B, C, D, E, F, G, H, I. It's got to try to find this entire pattern. The question mark here, question mark colon, says, you know, we need this as part of our pattern to match, but we don't want to actually capture, we don't want to extract it. So here's our string A, B, C, D, E, F, G, H, I, J, K, L, and we're going to match this entire pattern, B, C, D, E, F, G, H, I. And we want to extract out BC, we're going to extract out DEF, and we're not going to extract out GHI. If I do this, ABCDGH capital I, then we don't get a match because it doesn't match this literal lowercase I here. Okay, we get no match. All right, so let me just show you some more examples of this. Okay, here I've got a string that says Mr.Smith, comma, Mrs.Lee, comma, ms.Garcia, Ms. Garcia. Okay, and here the pattern is going to be MRS, capital MRS, or capital MS, or capital MR. And so when we do this, it's going to match. Okay, it matches the Mr., it matches the Mrs., it matches the Ms. here. It reads left to right. So if you had switched the order here to MR or MRS or MS instead of this order, what would it match? Okay, here it's going to match MR Smith, it's going to match MR Lee. So even though this is MRS Lee, it's going to match MR because it's reading left to right. It picks out the MR first and it says, ah, I've got a match, and it pulls it out. Okay, and then it moves on and it goes to MS and it extracts out the MS. Okay, because it reads left to right. And so it's going to find the MR first. It's going to pull that out and end there. So you have to kind of give it in this order, MRS, MS, MR, and it's going to find, when it finds the MR here, it matches this. Here, it's going to say MRS, and it matches the entire MRS pattern there. So, you know what, another kind of thing that you could do is you could just do MR question mark or MS question mark. And this says M and one or more, 0 or 1 R's, 0 or 1 S's. And so we will get, it'll find Mr., it'll find MRS, and it'll find MS, okay? The thing that this will also match that this won't match, it'll just also find a capital M by itself, capital M by itself, because it will be M followed by 0 R's and 0 S's. So this could be useful if you want to say, you know, I want to pull out people's last names, right? Mr. Smith, Mrs. Lee, Ms. Garcia. Here we've got Andy Hope out of nowhere. And we're going to say, all right, pull the kind of the title, Mr., Miss, Mr., okay, with a literal dot and a space and a word character, a bunch of word characters. And so here we find the pattern Mr.Smith, and we extract out Mr. and Smith. Mrs.Lee, we get Mrs. and Lee, and Ms.Garcia, and we get Ms. and Garcia. We don't get a match on Andy Hope because it doesn't match this pattern of Mrs., Ms., and Mr. Okay, and so this is why you might want to use a non-capture group, because maybe you're only interested in the last names, but you want to make sure that there is some kind of title of Mr., Mrs., or Ms. And so here, we're going to say we want to make sure we match this entire pattern of Mr. Smith, Mrs. Lee, Ms. Garcia, but we're not actually interested in getting the title itself. We're just interested in getting the last name, the part that follows the dot space. Okay, so here we're going to do, we get the match Mr. Smith, Mrs. Lee, Ms. Garcia, and we're going to just extract Smith, Lee, and Garcia. All right. So let me just show you another example using back references with capture groups. Okay, so here I'm going to say find kind of any sequence of connected word characters followed by a space, followed by another sequence of word characters, and maybe a comma. A comma question mark means comma 0 or 1 commas. Okay, these are in capture groups. So the first capture group becomes /1, and the second capture group becomes /2. My pattern is George Washington, comma, John Adams, comma, Thomas Jefferson. And what I can say is, all right, so if we run this, we're going to get George Washington, comma, and we extract out George and Washington. We get John Adams, comma, we get John and Adams. We get Thomas Jefferson, and no comma, nothing after that. And that's fine because we have a comma question mark, which means 0 or 1 commas, and we get the capture group Thomas and Jefferson. All right, so why would I want to use a back pattern? Is I could say, all right, find these matches and replace the match. So replace George Washington, comma, replace it with /2, replace it with the second capture group, comma, space, first capture group, semicolon. So what is this going to do? What this is going to do is it's going to find George Washington, comma, that's what it's doing, and it's going to replace it with Washington, comma, George, semicolon. Then it finds John Adams, comma, and it replaces it with Adams, comma, John, semicolon. And then it finds Thomas Jefferson, and it replaces it with Jefferson, comma, Thomas, semicolon. So it's dynamically finding these capture groups, this pattern, and it's using those and kind of rearranging things around. So if you want to kind of like take these into consideration and use them as far as kind of the replacement strings, you can do this. And so now This is what we have. We have Washington, George, Adams, John, Jefferson, Thomas. Okay. And so this gets a little bit complicated here. All right, here it says the quick brown fox jumps over the lazy dog. All right, and here, this is the pattern. So now it gets harder, but we're trying to understand, like, how do we read these regular expressions? Okay, this says we want a word boundary followed by a capture group of word characters, followed by a space, followed by a back reference to one, followed by another word boundary. Okay. Basically, this says find any instances of the same word repeated more than once. We have a word, space, and basically the same word. So it's going to find this instance of the. Okay, the pattern will match words that are repeated, right? So it's this word is the, and then the same word, a back reference to this. So the space the will satisfy this. Okay, so the quick brown fox jumps over the lazy dog. The will match here. The space the, reference back to whatever word it was here. All right, this is a more complicated thing, but this is something that could look like a phone number. So here we say, I want a literal opening parentheses, okay, and that's optional, okay, followed by a capture group and a consisting of the digits 2 through 9, followed by 2 more digits, because in the United States, there's an area code. Your area codes are not allowed to start with zeros or ones, okay? Area codes can't start with zeros or one. Okay, and then after the area code, you have the prefix, the first 3 numbers, and those cannot be 0 or 1, and then you have your last 4 numbers, okay? And so we're gonna say a capture group, and so this will match basically all of it's detailed out here. And so here's a whole bunch of text kind of, this is a vector of text. We have Apple, this number 1-800 something. We have a phone number here, another phone number with dots, a phone number with no spaces. Here, somebody wrote multiple phone numbers, work and home. Here we've got something that is not really a phone number because it starts with a 1. And then we say, yeah, I match this pattern. We don't get a match for Apple. We get a match for this. 800, we get a match for this. We get a match for 310 this. We get a match for this. We get a match for the work. It skips over the home. And we don't get a match for that last one. Okay. I could do string extract all, taking the same text. And what string extract all will do is it will say, you know what, if you find multiple matches in one instance, which is what we have here for work and home, extract both of them, okay? And so we get nothing for Apple and we get nothing for this last one, but we get both the work number and the home phone number here, okay, if we use string extract all. Now, what can be annoying is that when you have this and we say, you know, do the string match and you find this, you get, you know, this is, if you're like me, you look at this, this is bothersome to you just because all these phone numbers are in different formats. And so you might say, you know what, I want to clean this up a little bit, right? I want to clean this up. So here we can extract out the area code, and we can also extract out the following part, and we can try to pull these things out and kind of do a little bit of cleanup, right? So given that thing, we can go through all of the matches that we find, and here we've extracted out all of the area codes. We've extracted out the remaining phone numbers. Okay, and so that can get cleaned up, and you can kind of go through and replace any of these things, whether it's got a dash or a dot or no space or no spaces or a space, and you can say kind of, you know, I want you to clean this up. Take the prefix, you know, and either a dash, space, dot, any one of those things, make it optional, 4 letters, and then I want it to be replaced with kind of the first group dash the second group. And so all of these things will get cleaned up to be 786-100, you know, this thing 208.0448 will get replaced with 208-0448. This thing that had no space, 825-8430 will get 825-8430. This one had a space that gets replaced with a dash, and so on and so forth. So you can kind of have it go through and and clean things up. And that's better than just saying, find any instance of a space and replace it with a dash, or any instance of a dot and replace it with a dash, because it can still go through things where the dash or the dot doesn't even exist and establish and put in the dash between the third and the fourth digits in this sequence here, right? So this is where kind of capture groups and back references kind of work together to kind of clean up the formatting here. Okay. The last bit is look arounds and look behinds. I just have a couple examples, but you know, we'll just call it an end here. Okay. You can look over these slides. I will not put look arounds or look aheads and look behinds on the midterm exam. Okay, but you can expect other regular expression stuff to appear on the midterm exam, and other content from this lecture to appear on the midterm exam. Okay, so we will end here for today. Sorry for going long. Thanks for being patient, and thanks for sticking around. And have a good night. And we will see you guys next week. But also, yes, I will post the midterm exam on Friday, and you will have between Friday and Saturday to work on it. All right, have a good night. Thank you, everybody.